I'm not really going to talk much about that in general, but we're going to stick to a story we can all understand just by understanding hyperbolic structures on surfaces, and I'll try to indicate to you what the interesting generalizations are beyond that towards the end. Okay, so um, so let's start with a surface, a closed surface S oriented of genus G greater than or equal to 2. Okay, and this topological surface emits many different hyperbolic structures. I've drawn some here. And these hyperbolic structures are organized into what's known as the Teichmüller space of S. So I'm going to define that here. That's just the space of hyperbolic structures on S up to some equivalence. Okay. All right. So what is a hyperbolic structure? So let me give you sort of three equivalent definitions. Maybe the most common one, and if you haven't thought much about this, maybe the most natural one to think of now is just it's a Riemannian metric on S, which I'll call rho, with sectional curvature -1. Okay, so it's a constant negative curvature metric on S. Or equivalently, it's sure, which I'll also call rho, modeled hyperbolic plane in the sense that I defined yesterday in my colloquium talk. Just okay if you were not there. In other words, it's just a way to put coordinates on your surface where the coordinate hyperbolic plane, and so that the transition functions when you change coordinates are isometries of the hyperbolic plane of the Lie group PSL2R. Whoops. Okay, and finally, you can also think of a hyperbolic structure just as a representation of the fundamental group pi1 of S into the isometry group of the hyperbolic plane PSL2R. So yeah, so this is what's called the holonomy representation. It's injective and discrete, and every injective and discrete representation into PSL2R gives you a hyperbolic metric. So these things are all equivalent. So I'll say that it's this third perspective that's generalized in higher Teichmüller-Thurston theory. So what's a higher Teichmüller space? It's some sort of space, let me be vague, of special representations of the fundamental group of S into some higher rank semisimple Lie group G. And the only example I will talk about specifically at the end of this talk is just the case where G is the product of D copies of PSL2R. And for this group, a natural higher Teichmüller space that occurs is just the product of D copies of Teichmüller space, so D tuples of hyperbolic surfaces. Okay, so that's what I'll try to get to at the end. Okay, so Teichmüller space is a very beautiful object that's been studied for decades and decades. One nice thing we know about it is we know how to parameterize it in a nice way. So you can actually make all hyperbolic structures on our surface S very concretely. This is called the Fenchel-Nielsen parameterization of Teichmüller space. What do you do? Maybe I should ask, how many of you know about Fenchel-Nielsen coordinates on Teichmüller space? How many of you have never heard that story? Okay. So what you do is you choose a maximal collection here of pairwise disjoint non-isotopic closed curves on S. And that will be, turns out there will be 3G minus 3 of those. And those closed curves decompose the surface into pairs of pants. And each pair of pants can be equipped with a hyperbolic structure so that the boundary cups of the pants are straight, are totally geodesic curves. And it turns out the number of ways to do that is just parameterized by the lengths of these three cups. So there's a 3-parameter moduli space of hyperbolic structures on a pair of pants. So you put a hyperbolic structure on each pants, then you stick them back together in the pattern that you started with. And when you do that, there's actually a 1-parameter way to glue them together called a twist. You can glue them and then twist. And so that gives you another degree of freedom. So essentially for each curve in my pants decomposition, I get to choose a length and a twist. And that gives me 6g minus 6 independent real number, positive real number, well, yeah, numbers I can choose. Okay, so that's how I can see that the Teichmüller space is just a ball of dimension 6g minus 6. Okay. Anyway, you can make all the hyperbolic structures in Teichmüller space in this way. But of course, there's a lot of interesting things about Teichmüller space that are harder to see directly. Okay. All right, let's go on. All right, so given a hyperbolic structure on S, so I want to talk about a natural invariant of hyperbolic structures on S. So let's take a hyperbolic structure. So the invariant I want to talk about is called the length spectrum. It's a very natural thing to do. What I can do is I can take any free homotopy class of curve, like the one I drew on the surface there. It's maybe pretty complicated. I can pull it tight to its unique geodesic representative in the given hyperbolic metric, and then I can measure the length of that geodesic representative. Okay. So I do that for every. So in this talk, gamma is going to denote a free homotopy class of curves, or maybe also its geodesic representative. I'll be a little bit loose about that. But here I take a free homotopy class of curves gamma. I measure the length of the geodesic representative. That gives me a function from free homotopy classes of curves, which of course identify with the conjugacy classes in pi1 of S, to the positive real numbers. Okay, and that's called the length spectrum associated to a hyperbolic structure. Okay, so a hyperbolic structure determines a length spectrum, and conversely, the hyperbolic structure is determined by its length spectrum. Actually, knowing all of these lengths tells us, we can figure out what the hyperbolic structure is from that information. Okay, is that clear? Any questions about that? Okay, so all right, so that brings us to Thurston's asymmetric metric. So if I have two different hyperbolic structures, what's a natural way to compare how different they are? How do I compare them? Well, what I can do is I can take a free homotopy class of curves, gamma. I can measure its length in one hyperbolic structure. I can measure its length in the other hyperbolic structure, and I can compare how different they are, right? So let's take the ratio lambda rho 2 of gamma over lambda rho 1 of gamma. Sorry, I guess I didn't say this out loud on the previous slide. This function is called lambda rho, the length spectrum function. So that'll always be denoted lambda sub rho. Okay, sorry. Okay, so I take lambda rho 2 of gamma divided by lambda rho 1 of gamma. Okay, so that tells me how different the curve gamma looks in the two hyperbolic structures. And then I look for the most extreme that ratio can be. I take the supremum over all free homotopy classes of curves and look for the biggest discrepancy there. Okay. This supremum is going to be called C lambda rho 1 comma rho 2 throughout the talk. So I'm gonna use this notation again and again. So just remember, C lambda is the supremum of length ratios for rho 1 and rho 2. Okay, clear? Okay, does that seem like a natural way to compare two hyperbolic metrics? Okay. Okay, so from this, you can actually make a metric on Teichmüller space. So what do? You just take the log. You take rho 1, you take rho 2, and you take the log of C lambda. Okay, so it's abstract nonsense to check that this function satisfies the triangle inequality. It's non-trivial, but true that C lambda is bigger than 1 if the two hyperbolic metrics are different. Of course, it's equal to 1 if they're the same. And so taking log, I do get a non-negative function here, which is positive whenever we have two distinct metrics. Okay, so it satisfies, 2 out of 3 conditions of the definition of metric, and but unfortunately, it's not symmetric. If I take this ratio for rho 1 and rho 2, if I exchange the roles of the numerator and the denominator here, it turns out I don't get the same thing typically. The supremum is some other number. Okay, so we call this Thurston's asymmetric metric on Teichmüller space. It's a really beautiful object, and studying it has led to a lot of cool geometry, some of which I'll tell you about. And there's an interesting literature to dive into if you think this story sounds cool. Okay, questions about that definition? Yeah? Well, you have to do it in the right order. So the question is for Zoom people, how do you make sense of the triangle inequality for an asymmetric metric? You just have to make sure you write things in the right order. The distance from number 1 to number 3 is less than or equal to the distance from 1 to 2 plus the distance from 2 to 3. So make sure you just do that. Yeah. Other questions? Yeah. S is closed right now. Yeah. That's right. Yeah, there's a story here when S is not closed, like maybe S is has punctures or has convex co-compact ends. Let's not think about that right now. Okay, so I don't think about metric. I don't care about the actual metric. What I care about is this C lambda, this supremum of length ratios. So I really want to try to understand. I want to understand this quantity and what can we learn from thinking about it. Okay, so let me just to maybe give you a graphical interpretation that will be useful. Let me draw a picture of what we're doing here. So I have two metrics, two hyperbolic metrics, row 1 and row 2. I've drawn row 1 on the x-axis and row 2 on the y-axis. And for each homotopy class of curve on the surface, I'm going to pull it tight as a geodesic in row 1. I'm going to pull it tight as a geodesic in row 2, and I'm going to plot the pair of lengths as a point in the positive quadrant of the xy plane. Okay? So I plot all of these infinitely many points, and you can sort of see. I tried to give some accurate examples here. You can see in row 1 the blue curve here. Oh dear, don't do that. The blue curve is pretty long, but in row 2 the blue curve is a little shorter, and so the blue point that I plot is kind of below the y equals x line. On the other hand, the red curve here is very short in row 1. It's longer in row 2. So these red points, this red point here is of slope bigger than 1. Why did I draw more red points? Why are there extra red points here? Yeah, thank you. Well, this curve I've drawn here is a simple free homotopy class. It's a simple curve on the surface, but I can also, there's another homotopy class which just does that curve wrapping around twice, and its length, of course, is okay. And so for every point here, you're going to see periodic copies of it at the same slope again and again. Okay. All right. So what's C lambda? Well, C lambda I get pictorially by taking all of the slopes I see here, all of the rays through these points, and then taking the smallest closed convex cone that contains them. Okay, so this is this cone, which will show up again later, is called the Benoit limit cone. And what is C lambda? It's just the slope of the top boundary of this cone. It's just the steepest slope that occurs or occurs as a limit of the slopes I draw here for each closed curve. Yeah? What are the black dots? Yes. Question is, what are the black dots? They're lengths for pairs of lengths for other closed curves which I did not draw on the surface. It's just to indicate that there's more than 3 curves on this surface. There's countably many, and you need to plot all of them. I didn't try to draw all of them, but yeah. Yeah, so each black dot here represents some closed curve on the surface. It's the length in the first hyperbolic structure, comma, the length in the second hyperbolic structure. Yes, Sarah? The question is there any relation between C lambda rho 1, rho 2 and C lambda rho 2, rho 1? And the answer is not really. That's complicated. Yeah, they're not, in particular, they're not like inverse. They're not the same because, as I said, Yeah, no, it's hard to tell which one, how they relate. Yeah. Was there a question over here? Okay. Okay, so yes, the top boundary of this cone. Yeah. Yeah. That's a great question. So if I just take the set of rays through all of these points, in fact, if I take the closure of that set of rays, it will be a convex cone. So you will hit every, but in the limit, you will hit every direction in this cone. Yeah. Yeah. Oh, great question. The question is, as I draw these rays more and more for each curve, do the directions that I'm picking out equidistribute in this cone? Let me come back to questions like that. I'm not actually going to address that in this talk, but there's a lot of interesting work about questions like that. How do these points statistically distribute as you go out this cone, as you plot more and more points? Yeah, that's a really interesting question. Okay, so yeah, finish the punchline here. The slope of the top boundary of this cone is exactly c lambda rho 1 rho 2, and the slope, if you think about it, of the bottom boundary is 1 over c lambda rho 2 rho 1. Okay. All right. Good. All right. So this brings us to what I'm going to call today Thurston's simple theorem. Not to, pick on it, but Thurston's theorem says, okay, yeah, maybe I should have set this up better. A natural question is, as I'm looking for the supremum here, I'm plotting all these points, and I'm looking for the one with the biggest slope. Is there some natural subset of the curves on the surface that are more likely to see the, which curves on the surface really see the most extreme length behavior? And so Thurston's simple theorem gives a beautiful answer to that sort of natural question. It says that actually the supremum in the definition of C lambda is achieved over the smaller set of simple curves on the surface. Okay? So if I start measuring the lengths of curves a lot, I'm not to reach the extreme, I should really be looking for simple closed curves. Okay. So this theorem is like one of my favorite theorems in math. It's kind of a beautiful relationship between geometry and topology, right? We're measuring this geometric quantity, this length stretch ratio, and somehow topology is entering the picture, saying, yes, that's going to be achieved by simple curves. The sort of most natural class with respect to the topology of the surface of curves to look at. Okay. So I'm going to try to prove this theorem to you in a different way than Thurston did. But first, let me not get ahead of myself. Let me tell you roughly Thurston's story about this theorem. And that brings me to big idea number one. I'm trying to fit into the theme of the conference here. So this is a big idea that maybe it's a bit of a stretch. It's like not a new idea at all, but vaguely, if you're trying to optimize over some discrete set, well, that's pretty hard to do. It would be easier, it's often easier to optimize over, over a compact set, right? Compact is good for optimization problems. So we have an optimization problem over a discrete set. It's find the supremum of these length ratios, like plot all these points and find the steepest slope. So Thurston considered instead a different optimization problem, the following. So let's consider our two hyperbolic surfaces, rho 1 and rho 2. Let's consider all maps from the surface to itself in the homotopy class B, but thought of as equipping the domain with rho 1 and the range with rho 2. Let's consider Lipschitz maps with respect to those two metrics and try to infamize the Lipschitz constant. So let's look at maps between the first metric and the second metric and try to minimize the distortion of those maps, minimize the Lipschitz constant. Okay? All right, So we'll call this infimum, we'll call this C lip, the Lipschitz, the infimal Lipschitz constant associated to two hyperbolic structures on S. And it's an easy exercise you can do in your head right now probably to show that C lambda is actually less than or equal to C lip. Okay, that's elementary. But as I alluded to in my big idea here, we can actually solve this optimization problem. We can actually find that this inf is not an inf, it's a min. And in fact, there's a really nice optimizer. So this goes back to Thurston's 1986 paper. I'll also mention Kassel and Guéritaud, Kassel, who extend these ideas in the context of surfaces that have boundary or punctures and things like that. The theorem says that if C lambda is bigger than 1, which I told you it always is for two different hyperbolic metrics on a closed surface, then C lambda equals C lip, and there exists an optimal Lipschitz map F that stretches by exactly C lambda along a geodesic lamination, capital lambda, in the surface. Okay, who knows what a geodesic lamination is? Who does not know what a geodesic lamination is? Okay. So geodesic lamination, so it only makes sense a priori to talk about this with respect to a particular hyperbolic structure. In fact, there's a way to go between that. The same lamination can be made sense of in any hyperbolic structure, but let's come back to that. A geodesic lamination on a hyperbolic surface is a closed subset of the surface foliated by geodesics. So it's a bunch of geodesics running along the surface that make up a closed set, and these geodesics never cross one another. Okay, so let me give you a picture. Okay, before looking at this picture, the simplest example of a geodesic lamination is a single closed geodesic, right? That's a closed subset. It's foliated by geodesics in kind of a trivial way. I could take two closed geodesics as long as they don't cross. That's a lamination. Most generally, though, a lamination looks something like this. It looks kind of like a train track. Okay, so this picture is meant to look to you. We're sort of looking from far away at this lamination. It looks like just some sort of geodesic arcs. And then there's sort of vertices here where somehow two almost geodesic arcs come out at tangent and sort of split apart. And these tracks can merge as well. Okay, so that's sort of the fuzzy picture. What's the real picture? The real picture is that if you zoom in on this train track right here, what looked like one geodesic arc is actually two clumps of geodesics. Okay, and if you zoom in on either clump, each one is two more clumps, and et cetera, right? You see a sort of Cantor set behavior, a Cantor set cross-section where you see geodesics that are bunched very closely together in groups, sort of at all scales. And the point is, why are there two clumps? Well, here, this part of the train track is going to split when I come over here, right? So these two clumps are very close together, but they're preparing to split apart. So in negative curvature, essentially, if two geodesics are close together for a really long time, then they're super close together for most of that time. But eventually, as they're about to split apart, you'll kind of see a picture like this. All right. If you haven't seen a geodesic lamination before, I think it's one of the most beautiful objects that's kind of come out of Thurston's work in geometry and topology, and certainly worth learning about. They're beautiful geometric and dynamical objects with a lot of interesting features. Okay. All right, so how do we get from the existence of this maximally stretched lamination, how do we get Thurston's simple theorem? Any ideas? What do I do? I want to know that, I know that for our Lipschitz map, the maximal stretching is occurring along this lamination. What I want to know is that for the length ratios, I can achieve the optimum C lambda just by looking at simple curves. So how does this lamination suggest to me a sequence of simple curves? Any ideas? Okay, I'll tell you. So I can pick one geodesic in the lamination and start following it around. You know, maybe I do this a bunch of times and then okay. And eventually I'm going to come back to a place, it's not hard to believe in this example, where I'm very close to where I started. And then I can just close up. And remember, I've never, because it's a lamination, I've never crossed myself the whole time. I close up and I get a simple closed curve. And you'll have to trust me on this. Its geodesic representative is very, very close to the lamination. Okay? So I can approximate the I can take a leaf of the lamination, follow it around, close it up. I get a simple closed curve, and I do this for longer and longer times, and I get a sequence of simple closed curves that better and better approximates the lamination, and their length ratios tend to C lambda. Okay, because C lambda equals the Lipschitz constant for this map. Okay. Yes. Mm-hmm. Okay, I think the question is the question, why would there be some geodesic lamination which is stretched by exactly C lambda? The whole surface is not stretched by C lambda. So that's the point. We find this optimal Lipschitz map by taking some sort of Zela-Ascoli limit, right? And now we've got a Lipschitz map that realizes the best possible Lipschitz constant. And the theorem is, the interesting part is, yeah, most places on the surface the Lipschitz are contracted by more than that Lipschitz constant. A lot of the surface is crushed down really small by that Lipschitz map. But because we took this limit and we're pulling this surface as tight as we could, there has to be some part of the surface that is stretched by exactly this Lipschitz constant. And I'm telling you that part of the surface is a lamination. That's what's preventing you from making the Lipschitz constant even better by crushing more. Yeah. Yeah. Okay. All right. So we get Thurston's simple theorem from this. That's great. We can approximate the supremal length ratios by over simple closed curves, but we actually get more. In fact, we get what I'll call corollary 2 here. In fact, the lengths of these simple curves that I described, gamma n, their ratio is not just converging to C lambda, but in fact, this holds. If I take C lambda times lambda 1 and compare that, take the difference with lambda rho 2, then in fact that difference is going to 0, and it's actually going to 0 exponentially fast. So pictorially, what that means is if I start plotting the slopes, the pair of length for each of these simple curves, gamma n, in the corollary, not only are there slopes approaching the top, the supremal slope, but the actual points are getting very close to this wall. They're getting exponentially close to the wall. So it's a much stronger approximation result that you actually get here. Okay, why do you get that? Well, because, I'll say this in a vague way, laminations have exponential self-recurrence. Okay, so when I follow a leaf of a lamination around, the recurrence behavior that it exhibits is way stronger than you have any right to expect just for the usual geodesic flow on the tangent, the unit tangent bundle of a hyperbolic surface. Okay, so that brings me to big idea number 2. Extremizers are dynamically well behaved. Again, I mean, this is super vague, but I think many of you can probably think of examples of where something like this is true. So I'll just keep it vague. A lamination, which is showing up as an extremizer here, has super good recurrence properties, and that's, I think, kind of not an accident. Yeah. Okay, the question is there a dynamics or geometry interpretation of the alpha there? Oh, that's a good question. Probably, I don't know. I don't know off the top of my head. Maybe, yeah. Yeah, is it some sort of like Lyapunov exponential? Yeah, right. I don't know. I don't know. I think we could calculate what it is. It sort of depends on just the hyperbolic plane. Yeah. Yeah. Okay. Any other questions? Okay. So, all right. So I want to continue to focus on Thurston's simple theorem here, and I'm going to try to give you a slightly different proof, one that will hopefully generalize to the context I'm really interested in at the end. And it's not going to involve Lipschitz maps at all. It's only going to examine these closed geodesics on the surface more directly. So this is not what Thurston did, but secretly it's not so different. But let me try to explain. So okay, so here is a closed geodesic on my surface. It crosses itself, evidently, yes. And I want to try to explain to you why this closed geodesic could not be realizing the extreme, the supremal length ratio. Okay, so we're going to do a little bit of geometry here. Okay, well, what can I do if I want to take a curve that crosses itself and make it simpler? I can resolve a crossing. I can look at, let me go back. Here was a crossing, right? And I can say, okay, let me do this. I'm going to cut the crossing apart like this. So I'm going to turn this curve, I'm going to send that curve, that arc that way and that arc that way, instead of letting them cross. That's a new homotopy class of closed curve. It's now represented as kind of mostly geodesic, but with two sharp turns. And what I can do is I can then pull that geodesic tight again. And so basically this corner pulls tight to something that looks like that, and this corner pulls tight to something that looks like this, okay? Okay, so I resolve the curve, the geodesic, at one crossing, and then I pull it tight again. It's a natural idea. You guys have seen this sort of idea before. Okay, and what happens when I do that? Well, the length gets shorter, right? I had a geodesic, I modified it, and then I was left with a curve that is no longer a geodesic because it has these corners, but it had the same length. And then I pulled it tight. I pulled all the slack out of that corner. And I got a new geodesic, which is shorter in a different homotopy class. How much shorter? Well, in fact, this is where some hyperbolic geometry comes in. How much shorter depends on this angle, the angle at which the two arcs crossed. So call that theta 1. I claim that the difference between the length of the new curve and the length of the old curve is 4 log sine theta 1 over 2, exercise for anybody that knows some hyperbolic plane geometry, plus an error term, which goes to 0 if gamma is getting very long. So this error term might be appreciable for any particular gamma that we look at, but let's assume gamma is really, really long. And this is small. Okay, I'm going to call this quantity the slack. Again, you're imagining taking a geodesic, taking a crossing and rearranging it so that it's now a broken geodesic, and then pulling all the slack out of that rope so that it becomes geodesic again. Okay? Okay, so let's now imagine, oh, okay, yeah, right. So I do this again on surface number 2, on hyperbolic surface number 2. Yeah. Oh, good question. Yeah, my picture's a little misleading, isn't it? So the question is the geodesic, I think what the question is the geodesic representative of gamma prime actually just like one new arc here and then it actually connects up with gamma from before? No, that's not true. That's not true. But what's true is, remember, geodesics which are close for a really long time are super close for most of the time that they're close. So this picture is meant to suggest that yes, gamma prime looks very different near this crossing, but then it gets really close to where gamma used to go, and they run together for the rest of the time in the surface, like so close that your eyeballs can't even tell the difference. Yeah, but they are not, you're right, they are not exactly equal, outside of this region. They run very close together through the rest of the surface. Yeah, good question. Other questions? Yeah. When I do this resolution, could a new crossing appear? No, it can't. Yeah, so that can't happen. Could you get two different curves? You can, yeah. So that'll be the next case. Let me answer that in a minute. Okay, but let me just say, so you do this in the first surface, you do topologically the same thing in the second surface and measure what happens to the geometry. You get another slack formula here. It's the same formula, except now since the angle is potentially different, theta 2, you get a slightly different slack, right? And so now let me convince you, if the supremum, let's say this blue gamma I've drawn actually is a curve realizing the supremum, the maximal possible length ratio. And let's assume that theta 1 is less than or equal to theta 2. Well, what do we know about this function? 4 log sine theta over 2, calculus time. It's monotonic, increasing, right? Okay, so ignoring this error term, if theta 1 is less than or equal to theta 2, then slack 1 and slack 2 are such that if I draw them as a vector, so they're both negative, right? Both the curves are getting shorter. But if I draw them as a vector, it has slope. It has sort of negative slope. Well, sorry, it has positive slope, I guess, but smaller than 1. Okay, this is a little confusing, but you can trust me that I've got the monotonicity right here. So if I think of starting with gamma and plotting its two lengths as a vector, I then do this modification that its length changes by this vector, this slack vector, in the negative direction with slope less than 1. Because the slope of the pink line was bigger than 1 to begin with, I actually get a new vector, the pair of lengths for my yellow resolution, which is steeper. Okay, contradiction. That cannot happen, right? Because gamma, we assumed gamma was realizing the maximum stretch. Okay, so by examining this resolution, we get a contradiction. Contradiction to the fact that gamma crossed itself. Okay, does that make sense? Okay, you might say, well, okay, but what if theta 1 is not less than or equal to theta 2? And of course, there's another case, as was suggested already. In fact, if theta 1 is bigger than or equal to theta 2, we're going to do the other possible resolution. We're going to cut this crossing like this. Now what happens is we get the resulting object we get is not one closed curve, but two closed curves. You can check. Okay, it might seem like the situation is symmetric, but note that I've drawn these arrows here. So the curve is going like this and then like this. So that's why they're different. So you get two curves, gamma double prime and gamma triple prime. You pull those tight in both hyperbolic structures. You measure now the difference in total length up here. And now the slack is up to an error term going to 0, 4 log cosine of the angle of intersection over 2. And okay, sine is increasing for theta between 0 and pi over 2. Cosine is decreasing, thank you. Cosine is decreasing, so this is the right thing that we want for this situation here, theta 1 bigger than or equal to theta 2. And so indeed, if we take the vector value, the sort of vector of pairs of lengths for gamma, and compare it to the sum of gamma double prime and gamma triple prime by the same argument as before, that sum will have slope outside of the cone. So one of them has to have slope outside of the cone contradiction. Okay, it's the same argument, slightly more complicated because there's two curves, but okay. Okay, so I call this kind of argument a slack calculus. It's, I don't know, maybe an abusive terminology, but you're calculating the slack when you resolve a crossing and you pull out the slack. How does the length change in structure 1 versus structure 2? Can actually be estimated really well, and you can do this type of argument. All right, any questions about this? Okay, so I think I need to speed up a bit here. So A, you might ask, okay, but what about these error terms? Because if the sup is realized by gamma, how do we know gamma, how do we know how long it is? It might not be very long. And I say that's okay, because you could just take powers of gamma. You can just run around gamma 35 times or 1,000 times until it is long enough for this argument to work. Okay. Still, if you run around 35 times, you get 35 copies of the same crossing. Only resolve one of those crossings, and leave the other 34. And do this argument, that's fine. Okay, so this works. But more importantly, you might say, Jeff, what if the sup is not realized? Probably it isn't, right? In fact, probably it is. That's another story, but certainly there are many times where it is not realized. So what do you do? Okay, so if the sup is not realized, then C lambda can only be described as a limit of a sequence gamma n over a sequence gamma n of steeper and steeper length ratios, right? So we return to big idea number 1. We'd like to take the limit of these gamma n's. I don't want to use Lipschitz maps in the way Thurston did. I just want to take a limit of all these closed curves. That doesn't really make sense, right? How do you take a limit of homotopy classes of closed curves? Okay, so here's a way to make sense of that. It's called geodesic currents. And I know some of these are near and dear to some of you. So let me try to say very briefly what a geodesic current is. So if I have a curve gamma n, let's take its geodesic representative. I can replace that single object, that curve on the surface, with a measure. I can replace it with the length measure, we'll call it mu n, along the lift of gamma n to the unit tangent bundle of S. Okay. Okay, so now I've got the unit tangent bundle. I've got its geodesic flow, and associated to a closed geodesic gamma n is a periodic orbit of the geodesic flow. Okay, and I take that periodic orbit and I put the length measure localized on that single orbit. Okay, so that's now a measure. And the point is that spaces of measures have good compactness properties. Okay, I can usually take limits of measures if things are nice enough. And so I can actually do that here. So if I take this mu n and suitably rescale it, it actually converges to a limiting measure, mu infinity up to subsequence. And that limiting measure is now some measure on the unit tangent bundle of S, supported on some collection of geodesics. Now maybe not a single closed orbit, but some subset which is invariant under the geodesic flow. So generally, a geodesic current is a geodesic flow invariant measure on the unit tangent bundle. Okay, that's what it is, and that's actually the appropriate space to take limits of closed geodesics. Okay, who's seen geodesic currents before? Who has not? Okay, again, this is a very powerful piece of machinery. It goes back to Bonohan, and it's sort of prevalent in the study of Teichmüller space and higher Teichmüller spaces. Okay, so I recommend you check that out. Okay, so all right, a few basic facts. The projectivized currents are compact. They're not actually. It's really a cone in an infinite dimensional vector space. It's not. The currents aren't themselves compact, but if you projectivize that cone, it's compact. Weighted closed curves are dense. Okay, so the types of limits we just described actually give you every possible current. And the length function extends continuously to the space of currents. So I can actually make sense of measuring the length of one of these measures. Basically, mu n was a limit mu n was a length measure supported on a closed orbit. Just like the total mass of that measure is the length of that closed geodesic. So the total mass of any geodesic current gives you a notion of its length. Yeah, we can make them probability if you want, but so no, don't make them probability. Sorry, finite. Yes, right. Yeah, we don't want to normalize them because then we lose the information about their length. Yeah. I should say for you, Walter, there are two ways of talking about geodesic currents, and this may be the other one than the one you're more familiar with. Yeah. Okay. Okay, great. Yep. Yes, the space of probability currents is compact. Yeah, I don't want to restrict myself to probability currents. I mean, it's the same. You're right. Yeah. So, yeah. That's right. Okay. All right. Good. So, oh yeah, I should point out inside of the space of currents. Sorry, when am I supposed to go until? 5 minutes. Okay. So inside of the space of currents is a very nice finite dimensional subspace called the space of measured laminations. We already saw what a geodesic lamination is. A measured lamination is a geodesic current whose support is a geodesic lamination. So all the geodesics in the support of this measure, if you project them down to the surface, they are a lamination. None of those lines cross. Okay, so that's a measured lamination. And so what do we want to show? To show Thurston's simple theorem, we'd like to show that the limiting measure, if I take these closed curves that are approximating the steepest possible length ratio, and I take their limit in the space of currents, I'd like to show that that limiting current is actually a measured lamination, okay? And then we can conclude that the gamma ends, maybe they weren't actually simple, but we could replace them with simple curves. Okay, that's almost true, but to conclude that, and this is kind of one new idea here that differs from Thurston's original proof. We need a cool argument that I learned from I should say, right now I'm kind of talking about classical stuff, but these arguments are all part of joint work with François Guéritaud and Fanny Kassel, and I learned this argument from François. We call it the record breaker argument. So in order to conclude that the limiting current is a measured lamination, you need to assume that each gamma n is a record breaker. Okay, and what that means is that each gamma n I've chosen in my sequence has steeper slope than any other curve which is shorter than it. Okay, so the length ratio for gamma n is actually bigger than or equal to the length ratio for any eta which is shorter. So I'm constructing a sequence approximating the maximal slope in the most efficient way possible. If I could have chosen a shorter curve with steeper slope, I did. Okay, so I'm going to choose one record breaker and then look for another one that's longer. And each time I choose a new element of my sequence, it has a steeper slope than anything else that was shorter than it. Okay, and so now I can kind of do the same thing we did in the previous case. If I assume that the limiting current, mu infinity, has two crossing geodesics in its support, you look at how those geodesics cross in both hyperbolic structures, angle θ1 and θ2. And because the support of this limiting current has a crossing, that means that all of the gamma n's cross themselves in almost the same way many, many times. If that didn't happen, then we wouldn't see these geodesics in the support. And so now you can take that really, really long gamma n that's crossing itself, in the same way over and over again, and resolve just one of those crossings in the two possible ways, depending on whether θ1 is bigger than or smaller than θ2, and do the same sort of slack calculus argument from before, and see that if gamma n is long enough so that the error term is negligible, then actually this crossing that it's doing is a contradiction, because from the slack calculus argument, we actually could have picked a shorter curve, either gamma n, sorry, these are numbered differently, gamma n prime or gamma n double prime or gamma n triple prime, shorter curves which actually have steeper slope, contradicting the record breaker property. Okay? Okay. All right, so I don't have much time, but I want to try to say some of my own results here. I hope this was at least somewhat understandable kind of introduction or a description of a new way to prove Thurston's simple theorem. What I really wanted to talk about, which I'm running out of time for, is a generalization of this problem to the setting of d-tuples of hyperbolic structures. So now, instead of taking two hyperbolic structures, obviously the natural thing to do if you're trying to construct a metric on Teichmüller space, like forget about a metric, I don't care, I just want to take d hyperbolic structures and compare them all at once, okay? So what do? I get an RD valued length spectrum, right? I can for each closed curve gamma, I can take the length in each of the d hyperbolic structures, so I get a d vector. So I regard this as a vector valued length spectrum. And now I can plot all those lengths in the positive ortho of r to the d. So here's an example for d equals 3. I'm not good at drawing cones in R3, so I just projectivize the picture. And you see something like this. Okay, these are all the points, and they fill out some cone that looks like that. And the natural question, analogous to Thurston's simple theorem, is what types of curves on the surface or sequences of curves are seeing the boundary of this cone? Which curves are seeing the most extreme behavior for this length relationship? Okay, and let me say this cone is a generalization, or sorry, a specific example of something that's called the Benoit limit cone. It's defined for any representation of let's say a finitely generated group into a semi-simple Lie group. There's a notion of vector valued length in any such situation, but let me skip all this, unfortunately, and tell you at least one theorem, hopefully two. Again, joint with François, Guéritaud, and Fanny, Kassel, we show that if you have a d-tuple of hyperbolic structures on S, whose limit cone, this pink cone, is denoted L, and you have some supporting hyperplane to the boundary of this cone, call it omega, which intersects the boundary at one point, or one A, call that ray tau, then if this condition holds, namely omega 1 plus omega 2 is positive and the rest of the omegas are positive, then it turns out that this tau, this point on the boundary of the cone, is realized by some measured lamination. It is the vector valued length of some geodesic current mu. That's true in general, but that mu happens to be a measured lamination. Okay, so on the boundary of this cone, we are seeing some of the extreme points realized by measured laminations. Here's a picture of what this condition means. In fact, all of these points in this picture are realized by measured laminations. Okay. Is it true that every point on the boundary is realized by a measured lamination? No, that's not true. And then let me just end by stating main theorem 2. Well, okay. Yeah, let me say that this theorem is very specific to PSL2R cross PSL2R dot 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 cross PSL2R. For a general semi-simple Lie group, for those of you that think about higher Teichmüller Thurston theory, we don't actually have any result that finds measured laminations on the boundary of the Benoit cone. But in general, we can actually do something related. And here's main theorem 2. Let me end with this. So again, I have a d-tuple of hyperbolic structures. Its limit cone is L. I have a supporting hyperplane omega, supporting the cone along a single ray tau. So if we look at tau as a vector and pick out its unique minimizing coordinate, supposing that exists, and the corresponding coordinate of omega is not 0, then again we can say something about the type of geodesic current that realizes this point on the boundary. It's actually a measured quasi-lamination if omega I is positive, and a measured anti-lamination if omega I is less than 0. And further, we get that the approximation of the boundary at this point is exponential. So it's not just approximating in slope, but it's actually getting exponentially close to the kernel of omega. Okay, and importantly, there was not a version of main theorem 1, there is a version of main theorem 2 in sort of the general setting of higher Teichmüller Thurston theory for positive representations. Okay, I should stop, but I think I need to just show you a picture of what a quasi-lamination is and an anti-lamination is. So, yeah, okay. Okay, so yeah, before I do that, in this picture, we can actually, from this theorem, we can identify, we can say something about the behavior of all boundary points except a few key ones. All of these ones are quasi-laminations, quasi-laminations, quasi-laminations. These are anti-laminations here. You can see they're kind of in the weird part of the cone that's sort of, facing the wrong way. It's kind of on the wrong side of this midpoint here. And then at these points here, where we're crossing these walls I've drawn, we don't know how to say anything. So we don't know how to characterize the entire boundary, but big chunks of it we can. Okay. All right, finally, here's what a quasi-lamination and an anti-lamination are. So a measured quasi or anti-lamination is just a current whose support is a quasi or anti-lamination. Quasi-lamination is just like lamination. It says that geodesics that run together for a very long time don't cross each other and then eventually diverge. So two geodesics that get epsilon close in the unit tangent bundle don't cross. So the picture looks like this. It looks just like a normal lamination, looks like a train track, except there can be crossings at big angles. Okay, so it's like a lamination that can come back and cross itself transversely. Okay, an anti-lamination is a bit weirder. Again, it can have transverse crossings, but it has the weird property that two geodesics that run together and get very close for a long time, they have to cross. Okay, so this is something that's, I think, very unnatural to think about from the point of view of like Thurston, Teichmüller geometry. And I've never seen these things come up before, but they naturally come up here. These curves that run close together and then cross before they split apart. So they're appearing naturally on the boundary of the limit cone in this story. Okay, I apologize for going over. Thank you very much. Be happy to tell anybody more about this at a later time. There's a lot more to this story.
Hey, I hope you don't mind if you have questions for Jeff, if you can ask them during our break, right? So actually, you went right to the break. It's good timing.
Oh, okay, good. I could go longer if you.
We have a half-hour break, right? So you can ask some questions out there. If you have questions for any of the speakers yesterday, hopefully they'd also be open to questions out there. So can we talk for Jeff one more time? Yeah.
Thanks.
Hold on, I have 4 fast enough. Also, thank you again.
Should I leave?
Right, there's snacks and coffee, but like very importantly, we ordered lunch today. I don't know if you saw that email. So like when it's lunchtime, don't run away. There's halal guys. We also, please email us for reading groups. Please. We're trying to fill out a couple, like some people have asked us, we really want to fill out a group for them. So if you want to join a reading group this semester, send us an email at bigideasanddynamics@gmail.com. And very importantly, we want a picture of you. Right? Could we take a picture after Marissa's talk? Well, actually, I'll say we will be taking a photo after Marissa's talk, but you may leave and not be in it if you wish. All right. Thanks. See you back in here at 10. No, 11.